Here's a solution for homework 10 question 2. This question is collects the definitions of properties of stochastic processes. The first one is wide-sense stationary processes. A stochastic process is called a wide-sense stationary process if its mean is constant and autocorrelation is a function of time difference, which is like this. WSS is only uses mean and autocorrelation. In practice, they are much easier to get than second order density. So based on the mean and the autocorrelation function, we can do many things, like state estimation, parameter estimation, and prediction. In the communication application, we usually care about the power of the signal. The autocorrelation function Rt1 T2 is the average power of the signal at T1. So we say that if the input is a WSS process, the output of a stable LTI system is also WSS. The second stochastic process is independent increment process, which means xt1 minus xt2 and xt3 minus xt4 on non-overlapping intervals are independent. The Poisson process and the random walk and the Wiener process are all independent increment process. So it means independent increment property is related to Markov process. The third one is the Markov process. If the process xt is a Markov process, if the past has no influence on the future, when the present is no. So far we see that the Poisson process, the Poisson impulses, semi-random telegraph, and random telegraph, random walk, and Wiener process are all Markov processes. The fourth one is the normal processes, which also called the Gaussian process. A process xt is said to be normal if the random variables xt1, xt2, xtn are jointly normal for any t1, t2, tn. That is fx t1 to t1, t2, tn, x1, x2, xn is equal to this formula. The statistics of a normal process is completely determined in terms of its mean, sigma t, and autocorrelation Rt1, T2. In general, sigma t is a function of t, and in this Wiener process is one example of stochastic processes, and normal process is a property of stochastic processes. So we treat a normal process as a larger class of stochastic processes and treat winner process as a specific example. The fifth one is a strict sense stationary process. A process is said to be a strict sense stationary process if its statistics is not affected by a shift on the time axis, which is requires that the fx, x1, x2, xn, t1, t2, tn is equal to fx, x1, x2, xn, t1 plus epsilon, t2 plus epsilon, tn plus epsilon. This condition is hard to meet. The sixth one is white noise, which is defined as the mean of the white noise process is equal to 0, and the autocorrelation Rx T1 T2 is equal to Q_T1 multiple lambda T1 minus T2. Thus, next process is mean ergodic processes, which is defined as the limit t goes to infinity 1/2t multiple integral from minus t to t of xt dt is equal to the expected value of xt in mean square sense. In mean square sense is one kind of consistency. The last one is the martingales. A stochastic process xt is said to be a martingale if the expected value of xt given x s equal to x1 is equal to x1. S is smaller or equal to t. This definition means the conditional mean squares conditional mean equals the condition, and this is also true for random walk and winner processes. So this is the solution.